Hello, everyone. We are Team 1129 from Roger Williams University. I'm Drew. We've got Peter and Mike. Our coaches, Dr. Hasala, Gallolu, and then we chose SCUDEM Project B, an AI Ouroboros math model. So a brief overview, generative AI systems like ChatGPT learn by training on enormous amounts of online text and images. But as AI-generated content becomes more common across the internet, these models increasingly end up learning from their own outputs. This creates a kind of feedback loop where each new generation of models is trained on data that is less human and slightly more synthetic. Over time, this leads to measurably decline in quality, creativity, and accuracy, a process known as model collapse. Our project focuses on modeling what happens in a more realistic scenario, an ecosystem where multiple AI models interact alongside new human-generated content. With our preliminary research, we have one main core question: how will the quality of content generated by an AI change when the proportion of human-generated versus AI-generated content within the training pool changes? To answer that, we first needed a way to measure quality. For us, that means quantifying things like coherence, diversity, and similarity to human writing. Then we study how that quality changes as we vary the proportion, mostly from human data to mostly AI data. Finally, our model treats humans' data as positive injection that refreshes and stabilizes the system, while repeated AI to AI training acts as negative force, pushing the system towards what we call a model collapse.
So after reviewing the existing research on model collapse and recursive AI training, we wanted to express this behavior mathematically. And so in order to do that, we have to define a system of differential equations. Here, alpha represents the amount of AI-generated content in the system, where alpha equals 0 means all the human content is human, and alpha equals 1 means it's entirely AI-generated. The function Q of alpha represents the content diversity, or how original/varied the information remains at each level of AI involvement. The first equation captures the push and pull between two forces. The term negative k q alpha shows the decay, meaning as alpha increases, the originality is lost at a rate proportional to k. The second term, lambda ph alpha, introduces recovery, where new human-generated content restores diversity. The second equation, pH of alpha equals 1 minus alpha, just expresses that relationship. As AI shares grows, the human share naturally shrinks. And now that we have our system, we can now try and find an explicit solution. By integrating the differential equation using integration by parts as well as a integrating factor, we get this complete particular solution. This formula expresses the content diversity directly as a function of the AI content portion alpha. Each parameter here has a clear interpretation. Q naught is the initial diversity of the content pool, the starting point before AI influence. K controls the rate of decay, and lambda determines the rate of human injection, or how much human creativity offsets that loss. And now that we have the model itself, the next step is to generate data that lets us test and fit it. The goal here is to simulate what happens as more and more AI-generated content mixes into a human content pool. Step 1, we start with taking real human text, and we're taking this text from an AG News dataset, a large, well-known corpus of human-written news and headlines and summaries. This serves as our ground truth, our reference point for high-quality, diverse human content looks like. Step 2 is we need to generate synthetic data using 3 different AI models: Tiny Llama, Phi 1.5, and Distill GPT-2. Each of these models represent a different level of AI sophistication, from older, smaller ones to more advanced systems. We have each model generate hundreds of short news headlines, style texts, and word pairs so that we can simulate what it looks like if online spaces gradually fill up with AI written material. And then step 3, we need to mix the two together. We mix human and AI text together in varying proportions using the parameter alpha. When alpha equals 0, that means the dataset is 100% human, and when alpha equals 1, that means the dataset is 100% AI generated and no human content is left, as mentioned in the defining the model. With these mixed datasets, we'll later use it to measure content diversity and fit our differential equation model to see whether the predicted class behavior actually shows up in practice. Once we run the Python script that'll generate this data for us, it'll result in a couple different types of variables. Essentially, we need ways to measure how quality and diversity of the text change as the proportion of AI content increases. So we'll use 3 main metrics to determine this: perplexity, KL divergence, and specifically distinct2 to fit the model. Starting with perplexity, this measures how predictable a piece of text is under a large evaluation language model. It's kind of like a fluency test where if the model is easy to predict, the perplexity is low, and if the text seems chaotic or inconsistent, the perplexity is a lot higher. Generally, you want lower perplexity, but in this case, low perplexity is actually what we don't want because that shows repetitiveness and model degradation. Next is KL divergence or the Kolbeck-Leibler divergence. This one compares how different the statistical word patterns or the n-gram distributions in our mixed data set are from the human reference data. If the divergence is low, that means the AI and human text are still linguistically similar. If it's high, that means the AI text has drifted away from human-like language patterns, a sign of linguistic divergence or collapse. So in this instance, a lower divergence is better and a higher divergence is worse. Because a higher divergence means that the AI is drifting from human-like language patterns. And then finally, distinct 2, which measures lexical diversity, basically how varied the vocabulary is. A high distinct 2 means the text is rich and varied, and a low one means it's becoming repetitive or degenerate, the same phrases showing up over and over again. This one is important because this perfectly encapsulates the quality of a language model or the diversity of its output. So a high distinct 2 means it is a well-performing language model, and a lower one means it is degenerating. After generating our data, we can now look at our defined metrics and see as they behave as we increase alpha. At alpha equals 0, when the dataset is purely human written, perplexity is relatively high. That's a good sign because it means this text still contains novelty and unpredictability. But as we replace more and more of the human text with AI output, the perplexity drops sharply. Moving on to KL divergence, we can kind of see the opposite kind of motion. Here, the values increase with alpha, which means the linguistic patterns in the mixed text are drifting farther and farther away from the human reference distribution. And now finally, looking at our distinct 2 diversity metric. This one's especially revealing because we can see a clear decline as alpha increases. High distinct 2 near alpha equals 0 means a wide, rich vocabulary, but by the time we reach alpha equals 1, that variety collapses.
Now for fitting the model, we used a Python script with nonlinear least squares fitting along with a bootstrap for confidence intervals. And our goal for this was to estimate our parameters that we saw earlier in the slide. And as we can see from Tiny Llama, the curve fit is smooth and closely aligned with the observed data points. And the confidence band, which is that gray shaded area, is quite narrow, meaning the model's parameters are estimated with high precision. And it serves as kind of a baseline of stability for us due to its high confidence intervals. And then we see sort of a drastic turn in Distilled GPT-2. The model fit is still decent, but it's got a much wider confidence interval. Some of the confidence bounds even drop below 0, suggesting instability or poor assignment between the model's assumptions and observed data. This could also mean Distilled GPT's outputs are noisier or less consistent due to sample variation. And then Microsoft Phi, this model's fit looks pretty strong, just like Tiny Llama. And the confidence intervals are also tight, and the MSE is low. And the fitted curves shape pretty well to the observed points. And this suggests sort of more replicable performance, meaning if we ran it a bunch of times, then it wouldn't really change even given certain inputs. So these are the parameter estimations for those graphs that we just saw on the previous slide. As we can see, the Tiny Llama and 515 MSEs are pretty close in value, while Distilled GPT is about 1,000th off from them. We can see all of the actual confidence intervals from low to high in this table right here. So we have the lambda estimation, the K estimation, and QO estimation for all three models. And then the lam 95 low and lam 95 high. That's the low and high intervals for the confidence level at 95%. Same goes for the K95 low, K95 high. From this, we can see that we get pretty close numbers for most of them, with some outliers like Distal GPT-2 for QO.
In the end, our results highlight one simple truth. Without steady human creativity feeding the AI system, even the most AI models will eventually begin to collapse inward. These are the two primary references that we used for our project. The first was given to us along with the problem, and the second being the data set that we used. Thank you. This is our presentation.